Good morning, all of you. Myself, Dr. PC Dikshit. Let me start the first unit of Engineering Mathematics Level 1, Vector Space. Topic that is a vector space. Let A plus B a field whose elements are called a scalar, and let U be a non-empty set whose element called a vectors. Then V is called a vector space over the field F. It is denoted by VF if it will satisfy the following conditions. Number one, V is an abelian group. So for abelian group, it will satisfy the following four conditions. First, we closures law. Let alpha and beta belongs to V. Then we can write this alpha plus beta belongs to V for every alpha beta belongs to V. Then it is called a closures law. Number two, associatives law. Let us consider three vectors alpha, beta, gamma belongs to V. So we can write this alpha plus beta in brackets plus gamma equal to alpha plus in brackets beta plus gamma for every alpha, beta, gamma belongs to V. That is called the associatives law. Third one is commutative law. Let alpha and beta belongs to V. Then we can write this alpha plus beta equal to beta plus alpha for every alpha, beta belongs to V. Fourth is additive identity. So let alpha belongs to V, then there adjust an element 0 belongs to V, such that alpha plus 0 equal to 0 plus alpha equal to alpha. For every alpha belongs to V, then 0 is called the additive identity. Number 5, inverse for additive. So let alpha belongs to V, then there adjust minus alpha also belongs to V. Then we can write this alpha plus minus alpha pre-addition or post-addition minus alpha plus alpha equal to 0 for every alpha belongs to V. Then V is called an abelian group. Also it will satisfy the second conditions multiplication composition with a scalar element over the field F. That means let A belongs to F, alpha belongs to V. Then we can write this A alpha belongs to V. Then we can write this A alpha belongs to V. Third condition is also it will satisfy the some following conditions. A alpha plus beta equal to, we can write this A alpha plus A beta. That means A belongs to F and alpha beta belongs to V. Second is A plus B into alpha. We can write this A alpha plus B beta, B alpha for every AB belongs to F and alpha belongs to V. Third one is A into V into alpha. We can write this A bracket V into alpha for every AB belongs to F and alpha belongs to V. Then it is called it will satisfy the following all these conditions. Then F plus dot is called a vector space over the field F. Now another definition of vector subspace. Let Vf is a vector space over the field F plus dot and W is a subset of V. That means be a non-empty set. Then W or WF is called a vector subspace of VF if W itself a vector space over the field F with respect to scalar multiplications and additions. So these are the two definitions, that is a vector space and vector subspace. Now again we define the linear combination of a vector space. Again we define a linear combination of a vector space. Let VF be a vector space over the field F plus dot, and alpha, the element of vectors alpha 1, alpha 2, alpha 3, and up to alpha n belongs to V, and that is a equal to a1, a2, a3, up dot dot an. All elements are the element of F. Then we can write this the conditions alpha equal to a1 alpha 1 plus a2 alpha 2 plus a3 alpha 3 plus dot dot an alpha n. Then that alpha is called a linear combination of a vectors alpha 1 alpha 2 alpha 3 alpha 1 alpha 2 and alpha 3. For example, for example, if vector alpha equal to 5 or 9 and alpha 1 2 and 3 alpha 2 5 and 6, then represent alpha as a linear combination of a vectors alpha 1 and alpha 2. So for its solutions, let a1 and a2 belongs to F. That means a1 and a2, these are the two elements of field, and a1 that is a 2 3, and alpha 1 alpha 2 that is a 5 6, or alpha that 5 9. That means it can be represented as a linear combination of alpha 1 and alpha 2. So by linear combination definition, we can write this alpha equal to a1 alpha 1 plus a2 alpha 2. So we can put the values of alpha 1 alpha 2, then it becomes alpha equal to a1 2 3 plus a2 5 9, a2 2 3 plus a2 5 9. So that means, and also we put the value of alpha, that is a 5 9. So after this simplifications, on comparing both sides, we get the relation or equation in a1 and a2. We get the two relation of a1 and a2. Then solve the value these equations, find the values of a1 and a2, and putting in equations 1, then we get the linear combination alpha equal to 5 2 3 plus minus 1 brackets 5 or 6. That is alpha is a linear combination. Most important, that is a linearly dependent or linearly independent vectors. Linearly dependent vectors is generally denoted by the LD, and the linearly independent vector denoted by LI. Linearly dependent vectors, let VF be a vector space over the field F, and let any alignment set A1, A2, A3, AN belongs to F, then it is called a linearly dependent if there exist a scalars a1, a2, a3 dot dot an belongs to F. Not all of zeros, some may be zero, then is called a linearly dependent vector such that a1 alpha 1 plus a2 alpha 2 plus a3 alpha 3 dot dot an alpha n equal to 0. That means applying these conditions, find the value of a1, a2, a3 and up to an. If all of not all of zero, some may be zero, then equation is said to be the then vector is said to be the linearly dependent vectors or linearly independent vectors. Let VF be a vector space over the field F, and let set S equal to all element of scalars, that is a1, a2, a3, an belongs to F, and S is called a linearly, then S is called a linearly independent vector if there exists a1, a2, a3, an, all elements belongs to field F are 0, such that applying these conditions a1 alpha 1 plus a2 alpha 2 plus a3 alpha 3 plus dot dot an alpha n equal to 0. Applying this condition, then find the value of a1, a2, a3 and up to an. If all values of a1, a2, a3 and an all of 0, then vectors are said to be the linearly independent vectors. Another example, for examples, are the vectors vectors alpha 1, alpha 2, alpha 3 and alpha 4. That means 2, 2, 4, 2 minus 2 minus 4, 0, 4 minus 2 minus 5, 2, 4, 2, 1, 6 is a linearly independent or not. So let us consider that is the four vectors alpha 1, alpha 2 and alpha 3, and also let the four elements of field F A1, A2, A3 belongs to F such that applying the conditions A1 alpha 1 plus A2 alpha 2 plus A3 alpha 3 plus A4 alpha 4 equal to 0. Applying these conditions, now here we put the values of alpha 1, alpha 2 and alpha 3. Then after the simplifications, on comparing, we get the four equations in A1, A2, A3 and A4. A4. So these are the four equations, that is a linear homogeneous equations. So we can write this in matrix form. The coefficient of matrix A equal to, that is a 2 2 4 4. In particular, we can write this in row form. 2 minus 2 minus 2 2, 2 minus 1 5 1 4 0 2 6. That is a coefficient matrix of above all four equations. Now here we applying the condition, find its rank. So applying the conditions, find its ranks. That means first we applying the condition R1 equal to R2 minus R1, R3 equal to R3 minus R1, or R4 equal to R4 minus 2R1. With the help of R1, make all element of C1 A21, A23 and A31 all of 0. With the help of R1, make all element of C1 are 0. Now again we applying the conditions, applying the row transformations, and the matrix is reduced in this echelon form, in which number of non-zero rows are 2. So therefore its rank is 2. What which is less than n equal to 4, and that means number of unknown. So that is a number of unknowns, non-zero element, that is number of unknowns. So now given non-zero following vectors, all these vectors applying the conditions of all of vectors is A. Therefore now prove that the all vectors 1 plus 1x 1 plus x square is a linearly independent vector space over the polynomials over the Lie number of field. So now here we consider a1 equal to 1, alpha 1 equal to 1, alpha 2 equal to x, alpha 3 equal to 1 plus x square. These are the three elements of vectors. Now here we let three elements of field a1, a2, a3. Now applying the conditions a1, alpha 1, a2, alpha 2, a2, alpha 3 equal to 0. So now I put the values of alpha 1, alpha 2, alpha 3 in this above conditions. So we get a1 into 1, a2 into x plus a3 into 1 plus x square equal to 0. Now after multiplication and simplification on comparing, find the value of a1, a2, a3. So here all values of a1, a2, a3 all equal to 0. So given system of vector space is linearly independent. So that is the more examples of linearly independent vector. Another is Another example is also let alpha, beta, gamma are linearly independent vectors of Vf, where F is a field of complex number. Then prove that number 1, alpha plus beta, comma alpha minus beta, or comma alpha minus 2 beta minus gamma are also linearly independent. Second one is alpha plus beta, comma beta plus gamma, comma gamma plus alpha are also linearly independent. So now here we given that alpha, beta, gamma are a linearly independent vector. So prove that suppose E1 equal to alpha plus beta, that is a vectors, E2 equal to alpha minus beta, and E3 equal to alpha minus 2 beta minus gamma. So now here we applying the conditions of linearly independent vectors A1 E1 plus A2 E2 plus A3 E3 equal to 0. Now put the values of E1 E2 and E3 in these conditions, and after simplification we get the three equations: a1 a2 plus a3 equal to 0, a1 minus a2 plus minus 2a3 equal to 0, and a3 equal to 0. Solving these two equations, find the values of a1 a2 a3. So all of 0, so that means e1 e2 in e3 belongs to li. That means e1 e2 e3 is a linearly independent vectors. Now, again we discuss the linear transformation or linear mapping or a homogeneous of a vector space. Of a vector space. Let Vf be a vector space over the field F. Let S is a subset of Vf. Then S is called a basis of Vf if S is a linearly independent vector and each vector of V is a linear combination of a finite number of elements of S. Every linearly independent, now here we note that the theorem, every linearly independent subset of a finite generated vector space of Vf for a basis of V. So that is a definition of a basis of a vector space. Now linear transformation or linear mapping. Let Vf and Wf be a two vector space over the field F, a non-empty T such that U to V is called a linear transformation of a linear mapping or a vector space or a linear or a transformation of U to V. Then T is such that T alpha plus beta equal to T alpha plus T beta for every alpha beta belongs to U. T A alpha equal to A T alpha for every A belongs to U. Or to combine 1 and 2, so we get the another relation: a alpha plus b beta equal to at alpha plus bt beta for every ab belongs to f and alpha beta belongs to b. These three conditions are satisfied, then given vectors, given mappings are said to be the linear transformation. For example, T is defined as V3 say V2 is defined as T x1 x2 x3 equal to x1 minus x2 or x2 plus x3. Then so that T is a linear transformation. Let x equal to x1 x2 x3 and y equal to y1 y2 y3. So first we find Tx plus y. So now here we put the values of x and y. That means T x1 x2 x3 plus y1 y2 y3. Now also we can write this x1 plus y1, x2 plus y2, comma x3 plus y3. Now applying the above definition, tx1, x2, x3, we can write this x1 minus x2 and that is comma x2 plus x3. So applying the above definition, so we can write this x1 minus x2 comma x1 plus x3 plus y1 minus y2 comma y1 plus y3. So we can write this tx plus y equal to tx plus ty. Also another, find the value of tax. So now we write the value of x. TA, x1, x2 and x3. Now multiplying by a, so that is a ax1, ax2 and ax3, comma. Applying the given rules or given conditions, also we can write this ax1 minus ax2, comma, ax1 plus ax3. After simplification, it becomes Ta alpha equal to A T x1, x2 and x3. That means AT alpha. So it will satisfy all these two conditions. Then given system T is said to be the linear transformation. Another example also linear transformation. If T is defined as V3 say V2 is defined as Txyz equal to Yz, then so that T is a linear. Let x equal to xyz, x1, y1, z1, let us consider, and y equal to x2, y2 and z2. So first we find the tx plus y. We can put the value of x and y. That means t x1, comma y1, comma z1 plus y, that means x2, comma y2 plus comma z2. Now after simplification it becomes tx plus y equal to tx plus ty. Now also find TAX, that means TAXYZ. Now I'll put the value of x. After multiplication of A, we can write this T equal to AX1, AY1 and AZ1. Applying the given condition T, AX, AY1 or AZ1, we can write this AY1 and AZ1. A common, so that we can write this AY1 and Z1. And by 1 z1, then we can write this a t x1 y1 or z1. That means tax equal to atx. So above condition satisfies the all these two conditions, hence t is a linear transformation. Another example, so that the mapping t v3 say v2 is defined as tabc equal to ca plus b. Prove that it, it is a LT, and linear transformation. So now here we let A equal to A1, B1, C1 and B equal to A2, B2 and C2. So now here we find T, A plus B equal to, now here put the value of A and B. That means T equal to A1, B1, C1 plus A2, B2 and C2. After addition, it becomes T A1 plus A2, comma B1 plus B2, comma C1 plus C2. Applying the above given relation, TABC, we can write this C A plus B. So we can write this C1 C2, comma A1 plus A2 plus B1 plus B2. C1 plus C2, we can write this A1 B1 plus A2 B2. So we can write this C1 A1 plus B1, comma C1 A2 plus B2. We can write this T A1 B1 C1, we can write this T A2 B2 C2. So Ta plus B, we can write this Ta plus Tb. That is the first conditions is will satisfy. Also another, find the second conditions Taa. So we can write this Ta. Now I put the value of A, that is A1 B1 comma C1. After multiplication it becomes AA1 AB1 and AC2. A, so here we are applying the rule TABC equal to C comma A plus B. It becomes A bracket C1 comma A1 plus B1. So we can write this A T A1 B1 C1. So TAA equal to ATA. So from 1 and 2, it is clear that given transformation is a LT. Is a LT.
स्टॉप भी तो करिए सर, रिकॉर्ड होता ही जा रहा है अभी।